In this video, we will learn about simple harmonic motion, damped harmonic motion, and resonance. Harmonic motion is the symmetric periodic movement of an object or quantity about a center position or value. In simple harmonic motion, displayed in the graph shown, we see a repetitive, constant oscillation over time. Notice that the amplitude of the periodic motion stays constant as time increases. These graphs can represent real-world situations. For example, this graph could be a representation of a clock pendulum swinging back and forth. In damped harmonic motion, displayed in the graph shown, the amplitude of the periodic motion decreases as time increases. For example, if you are on a moving swing and stop pumping energy into the swing will continue moving with a constant period, but the amplitude, the height to which the swing will rise, will diminish with each cycle as the swing is slowed down and eventually stops from the friction created by the air or between the swing's own moving parts. Resonance, displayed in the graph shown, occurs when the amplitude of periodic motion increases as time increases. It is caused when the energy applied to an oscillating object or system is more than what is needed to oppose friction or other forces and sustain simple harmonic motion. For example, if you pick up a rope lying flat on the ground and start shaking it up and down while increasing the range of motion and strength of your swings, you will see resonance. Now let's take what we have learned and apply it to an example. Part A. Graph the height function h of t equals 6 over t times the cosine of pi over 3t for 1 is less than or equal to t, which is less than or equal to 6. In the context of this problem, t represents time and h of t represents the height of an object as a function of time, which will be in seconds. We know that we will evaluate the given function for the whole number values of 1 through 6, so let's start by filling out the table accordingly. Now we can evaluate the function for each of the 6 values, starting when t equals 1 or after 1 second of time. When t equals 1, we have h of 1 equals 6 over 1 times the cosine of pi over 3 times 1. Notice that cosine of pi over 3 is equal to 1/2. Thus, 6 times 1/2 is 3. The point we generate, which will be used to graph the height function later, is 1, 3, because the x-coordinate is represented by time and the y-coordinate is represented by the height of the object after a given time. Following the same procedure, we now evaluate the function when t equals 2. So we have h of 2 equals 6 over 2 times the cosine of pi over 3 times 2. The cosine of 2/3 pi equals negative 1/2, and negative 1/2 times 6 over 2 is negative 3/2. In this case, the point we get is 2 negative 3/2. Continuing this same procedure for the rest of the table gives us the remaining points. So h of 3 equals 6 over 3 times the cosine of pi over 3 times 3, which equals negative 2. This gives us the point 3 negative 2. Then we have h of 4 equals 6 over 4 times the cosine of pi over 3 times 4, which gives us negative 3/4. So we have the point 4 negative 3/4. Next, evaluating at t equals 5, we have h of 5 equals 6 over 5 times the cosine of pi over 3 times 5, which is 3/5. So now we have the point 5 3/5. Finally, we have h of 6 equals 6 over 6 times the cosine of pi over 3 times 6, which is 1. So our last point is 6, 1. Let's plot the 6 points we found on the coordinate plane and graph the height function. The height function appears to follow a damped harmonic motion. Now, let's continue to evaluate this function for larger values of t to observe what happens. Part B. What is the height in feet of an object modeled by the height function h of t equals 6 over t times the cosine of pi over 3t after 30 seconds? After a minute. In essence, this problem is asking us to evaluate the height function for the values of 30 and 60. Units of time in this context are in seconds, so we converted 1 minute to 60 seconds to keep things consistent. First, let's evaluate the function when t is 30. Substitute 30 for t into the function and evaluate carefully. This gives us h of 30 equals 6 over 30 times the cosine of pi over 3 times 30, which is 1/5. Thus, the object modeled by the height function is 1/5 of a foot in the air at 30 seconds. Next, substitute 60 for t into the function and evaluate similarly. We have h of 60 equals 6 over 60 times the cosine of pi over 3 times 60, which equals 1/10. Thus, the object modeled by the height function is 1/10 of a foot off the ground at 60 seconds.